nice to be in Kiev again. It's wonderful atmosphere and hospitality, so thank you. And then, as you can see from the first page, the original part of the talk is all joint work with Margarita Mendes-Lopez and Pietro Pirola. And we've tried somehow to start, as the title says, a Brill-Noether theory for higher dimensional surfaces and possibly something for higher dimensional varieties. And so our results are far by being final. We are starting on this. But I think it's an interesting topic and hope you will find it so. So this is an outline of the talk. Doesn't really it's not worth spending too much time on this. You will see it. The only thing I just like, as you can see here, I just like to start by recalling the main facts of classical Brill-Noether theory, which means Brill-Noether theory is for divisors on smooth projective curves. Because this is a really well understood classical theory, and so it can serve as a guide for what kind of things we should look for. So all the talk will be about complex varieties and projective varieties also. And as I was saying, let me just give you a brief summary of the main facts of classical Brill-Noether theory. So we start with a curve, we could say of general type, of genus at least 2, and then you fix two non-negative integers, the R and D, and define the corresponding Brill-Noether locus. So D is the degree. You consider all the line bundles on L of degree D, and then these are parameterized by a connected component of the Picard scheme, and then you look at the subset of line bundles that have at least R+1 sections. And the basic properties of these Brill-Noether loci are as follows. First of all, there is a natural scheme structures on these loci. It's a fitting subscheme structure. And then it is possible to compute to give an explicit description of the tangent space to the Brill-Noether locus at some point L. As I've written there, if the number of sections of L is exactly what is required in the Brill-Noether locus, so R+1, then the tangent space is the kernel of this map that I've written down, given by cup product. You have a section of L, you take cup product with an element of H1 of X, and so you land in H1 of L. And of course, H1 of X is you can identify H1 of X with the tangent space to pick D at L, because this is the tangent space to the Picard scheme, which is union of translates of abelian varieties. So the tangent spaces are constant. And the geometrical meaning is quite clear, because this a cup product with a vector with a certain direction, H1 of X equals 0, means that the section of H0 of L deforms infinitesimally in that direction. So if all sections deform, you have a tangent vector. And for, I didn't write it down here, but for line bundles with more sections than expected, then you get a singular point. The tangent space is all of H1 of X. And this is, I've written it like this also because this is the formulation that extends immediately to higher dimension. But you can reinterpret this in the case of curves by using Serre duality. And then dually you have the so-called Petri map from H0 of L tensor H0 of Kx minus L into H0 Kx. This is just, you can say cup product, it's just multiplication of sections. And if you think just for a second, the tangent space is the H1 of Ox and H0 Kx are duals, vector spaces, and the tangent space is the annihilator of the image of the Petri map. So one defines this Brill-Noether number. The Brill-Noether number controls all the theory in the case of curves. It's written there, and I had trouble in memorizing this number. And I think the correct way of thinking about it, learned from Pietro, is this is just G minus
the space of matrices.
Or I like H0 times H1 otherwise, because as I was remarking, this is the minimum possible dimension of T. If the Petri map is injective, then that's when T is smaller, and by duality, this is the expected dimension of T. Anyway, you just remember the way you like it. It's just
so, Rita, you said it is G minus H naught of L times H1 of L.
Yes.
That's the thing that makes sense. Why don't you write it?
Sorry?
Why don't you write it?
Because it's not exactly, I mean, it's true if H0 is just expected. Because in the Brill-Noether locus you also have line bundles with bigger H0. So this is H0 times H1 in the generic case. Anyway, I'm glad I did not put you, made you sleep so early. You threatened me, you said you would go to sleep immediately. Okay, so it's good. Okay, so the first main theorem about Brill-Noether loci for curves is existence, which means as soon as the Brill-Noether number is non-negative, then the Brill-Noether locus is non-empty. And the dimension is at least that given by the Brill-Noether locus.
At least for each
number. Hmm? Yes, this.
That is for each curve.
Yes, I said let X be a curve. More about that later, okay? So this is the main theorem, and then the second theorem tells you more about the structure of this loci. Of course, if the dimension is 0, there's nothing to say, you just have finite number of points, but as soon as the Brill-Noether number is positive, it makes sense to try to understand what these loci look like. And the connectedness theorem tells you that the Brill-Noether locus is connected, it generates peak D, and I did not write this here, but every component has dimension at least equal to the Brill-Noether locus. And then that's a third very important theorem that I think that's what Fabrizio was thinking of, which is about moduli. So this, I didn't even write it here. This says that the Brill-Noether number computes exactly the dimension of the Brill-Noether loci if the curve is generally moduli. The reason why I did not write it here is that we are making an attempt at generalizing these two statements. And of course, even in the case, already in the case of surfaces, the question of how this loci vary in moduli is, I would say, out of reach. For lack of understanding of the moduli spaces. So I didn't even mention it in the slides, but that's of course a very important part. And let me just give you an idea of how one proves these two results so that we can see what are the challenges that we have when we try to generalize this. So you just fix X, you fix an L of given degree. Just fix the bundle. Then I take another divisor you could be more precise, but I just say effective and of very high degree, very, very positive, okay? And then you can write down the restriction sequence for H on the curve. I should have said, but of course this sequence takes place on the curve. Then you twist it by L plus H, and this is what you obtain.
And
so
L is the same L as before.
Just one L. Just same as before, I defined the locus. So just take any L and H, and then you can take cohomology. And you see, you have in the middle, you have a linear map between vector spaces, and H0 of L is the kernel, H1 of L is the co-kernel. So we have we have given a map that essentially computes the cohomology. And then, again, Fabrizio was going forward. If you let L vary, then you have, I've written, this map gives you a map of locally free sheaves on the Picard scheme. And the Brill-Noether locus is precisely the degeneracy locus of this map. So you see here that it's a fitting locus, it's the determinantal locus.
I think the map H naught L plus H to it is the middle map, which it's the middle map.
Yes, that's the middle map.
But it's not what you wrote.
Didn't I? Yeah, I think.
You have a map of local.
Right, sorry. Yes, thank you, sorry. I should have taken, let me use all the features here. Okay, so this is the map I should have written, and in fact I wrote this one, which is the wrong one. Thank you. Okay, so how does the proof of existence of connectedness go? Then you have this locally free shift map, and you want to know what the degeneracy locus looks like. And then I think the oldest approach was just write down everything explicitly, which of course is far by being simple, but it was done, and this is, I think, the original proof by Kampf and I think independently Klein and Laxov. I'm no expert actually on this topic, but if you are interested, you just look at the first book by Arbarello, Cornalba and Griffith Service, and they have a really nice detailed survey of all the results. Another possible approach is to look for positivity properties of these vector bundles, and this is what was done by Fulton and Lazarsfeld, and they not only recovered the previous result by proving that the bundle of homomorphisms from E to F is positive, but they also could prove connectedness. So what are the main points here that make this approach work? Pic D is a compact smooth variety, so you can do intersection. These are proofs by intersection theory, and so that's what you like to have, a smooth projective variety if you want to do intersection theory. And then the second really important fact that makes the method work is that all the cohomology of L is computed by this map from E to F, because on a curve you only have H0 and H1, and so it's enough to deal with a map of locally free sheaves. If you want to compute the cohomology of a line bundle on a variety of higher dimensions, then you have to deal with a complex. And of course, this is much harder. And just want to mention a bit, I've not written names here because there would be maybe hundreds of names in some cases, but just give you an idea of the kind of generalizations of this theory that have been considered by several people. So this is, I think the first one I've written down, you you work on a fixed curve and you replace line bundles by vector bundles, and you stable vector bundles in order to have a moduli space to work with of fixed rank and degree. And there's no school of people. I'd rather not mention names because I will certainly forget somebody important.
You should say VBAC.
VBAC, okay, all the group that revolves around VBAC is about this instance. And then in some papers, I think this is, I can mention because I know one paper has been done by Mitrovic and Laura Costa. They have tried to start the theory for a variety of any dimension, but they make this very important assumption that is hi equals 0 for I greater than 1. So in some sense, it's very similar to the case of curves, because again the cohomology is computed by a map between two vector bundles. And then there are many people again now, I don't know if Miles can help me with that as he did with VBAC, but really trying to extend the theory to singular curves. There are really many people working on this. And of course, this is related to compactifying the Jacobian in order to have something compact to deal with. And then there are also a combinatorial approach for you can define all the machinery involved, like genus, Brill-Noether number, sections of line bundles, combinatorically for graphs. And there are papers also giving Brill-Noether, I think a recent paper by Lucia Capolazzo, giving Brill-Noether statements in this setting, and then she's also able to go back and forth between stable curves and graphs. And of course, this is also very important generalization is looking, as I was more or less hinting, at cohomological support loci for line bundles. That means looking at the loci where not only the H0 jumps, but any of the HIs jump. And this is also being studied intensively, starting with Green and Lazarsfeld and other authors, but mainly, I wrote mainly for topologically trivial line bundles, or by Serre duality for paracanonical line bundles. We have very strong results, but in the special case of line bundles that are in peak 0 or numerically equivalent to the canonical bundle. Okay, so I think that's that. And we had, so our purpose was to try to develop a theory for line bundles on variety of dimension greater than 1. So I'll start with a smooth projective variety of dimension n. I recall the definition of the irregularity. All of you know it's the number of independent one forms on the variety. And just let me recall, I think, a little terminology that I will be using. I will need to talk also about the, no, I made a mistake here. It should have been in 2 steps. Okay, if the variety is normal, we define the irregularity as the irregularity of any desingularization. And then we say that X is maximal Albanese dimension if the Albanese map is generically finite. And I shorten this by saying Dmax equals to albdim. Albdim is the dimension of the Albanese image. And then an irrational fibration. I don't know if Fabrizio agrees with this terminology. I think maybe you call this higher irrational fibration. Maybe, but I put irrational fibration for short. So it's a map, it's a vibration, so it's a map with connected fibers, positive dimensional fibers from X onto a variety B normal of maximal Albanese dimension and what is also called Albanese general type. Namely, the irregularity is smaller, is bigger, sorry, than the dimension. And one special case of this situation is when B is a curve. Then when B is a curve, B is smooth, B normal, and we call this is classical terminology in surfaces also, an irrational pencil of genus B. The genus is always the genus of the base.
The point is that if the genus is 1, how do you call it?
An irrational pencil of genus 1, but there will be no irrational pencils of genus 1 in this case. Okay. So, yeah, right. Okay. So we give exactly the same definition as we gave before, namely, given, not exactly, let me explain it better. Okay, this time I fix the variety, I fix a line bundle, and then I fix R, which is the number of expected sections, and then I take all the etas in pick 0 such that H0 of L plus eta is at least R plus 1. So in fact, this is a translate of the previous definition. I gave it in pick D. That's why I wrote that the definition is non-standard. And this may look, I mean, I think an intrinsic definition usually looks nicer. But there are technical reasons for this that I think will become apparent later, because I have somehow to compare this locus with some subtors of pick 0. So the origin is important in some sense. Okay, so and just while in the curve case, the case of R equals 0 just means if...
You are assuming that L belongs to this WR.
Not really. That's the point. We'll see. No, but it's more convenient to write it like this. Of course, up to translation is the same thing, and all the questions I'm interested in...
Torsion translates, you should take a point.
Sorry?
If you have a statement like torsion translates, you must take
I don't.
Point,
I don't, because this will be a bit like the Brill-Noether law. Of course, first of all, we don't have so precise statements. But also, the Brill-Noether loci are more similar to those of curves, so they will not be union of abelian subvarieties in general. Okay. Now, what I was pointing out that while for R equals 0 is a sort of a trivial case in the curve case, because it's just effective divisors of a given degree, so it's the symmetric product of the curve. In the case already of surfaces, the R equals 0 case becomes it's much more interesting, because you are trying to understand. Basically, you are trying to understand when a certain curve moves in an algebraic family. And I think, okay, more about this later, yes.
In fact, historically, the first proof by Kempf was working on the symmetric, on the product of the curve, symmetrical. And the vector bundle was the approach of Kleiman and Lax. So the proof you gave was the one by Kleiman and Lax.
Yeah, as I said, it's possible because, you know, I went through the theory using the book by Alberello con Alba Griffith-Harris, but I'm really not an expert. So it's very likely that you are right. I'm certain, not very likely. Okay, so what we did a little study of the infinitesimal structure of this loci, similar to that in the case of curves, and we have some existence and connectedness result in the case of surfaces. And I will reverse the order here, and I think I'll tell you about two first, about the surface case. Okay, yes, I forgot to say this. This is number one is not, it has certainly some interest in itself, but there's an interplay between these two topics, because exactly for understanding whether L is or not in its Brill-Noether locus, we will need some of the results in one when we prove two. And so since the approach that is used for curves is not so easy to generalize for higher dimensions, as I've already explained, we tried to take a different point of view, a different approach of a proof of a Brill-Noether type result. So we start with an effective divisor on R variety, and then this time I wrote it correctly. Again, you write down on X the classical restriction sequence and twist by L plus eta, and you get this exact sequence. And then you take cohomology, and this is the corresponding long cohomology sequence. And you see, if H0 of eta and H1 of eta are 0, then I got an isomorphism in the middle. And this means basically that I can try to reduce the problem of studying the number of sections of L plus eta on X to studying the number of sections of its restriction on the divisor D I started with. So this is you can hope for some kind of inductive approach to studying the structures of these Brill-Noether loci. And of course this is possible. I said if H0 of eta and H1 of eta are 0, then you get this isomorphism. So in order for this approach to work, you need that this H0 of eta, of course, vanishes as soon as eta is different from 0. But you need to know that there are many etas such that H1 is 0. And in fact, this is a very important body of work by, first of all, Green and Lazarsfeld, and then now I'm going to summarize the known properties of this set V1 of the, we want, for our approach to work, we want the complement of V1 to be large. So we like V1 to be small. And the first main result is essentially by Green and Lazarsfeld, saying that all the so-called cohomological support loci have dimension at least equal to the index, the group you are looking at, if X has maximal Albanese dimension, and the components are translates of abelian subvarieties. And then I think the fact that these translates are by torsion points is due to Simpson. And in fact, as I was saying, we will not exploit this fact at all, but I find it so striking that I had to write it down in any case, because I think it's a very, very deep result. And then, if we make further assumptions on X, that is, that it has no irrational pencil of genus greater than 1, then we have a very good bound for the dimension of V1 of X. This is at most 1, and 0 is an isolated point. So this is a union of translates, of elliptic curves, some isolated points, and 0 is one of the isolated points. And this assumption that X has no irrational pencil is not very restrictive, because if X has an irrational pencil of genus greater than 1, then it has already some very strong geometrical properties. You can try to study such X's looking at the fibration. So somehow, in the general case, you don't expect an irrational pencil.
the ray spectral sequence of the vibration.
No, this is just philosophical. We do nothing of the kind. I was just trying to justify the fact that from now on I will always assume that there is no irrational pencil, and I was saying that I think that the general case, quotation marks, is when there is no such pencil. And in any case, you can use different techniques to study this case. So it was a disclaimer. Okay, what are the problems in this approach? I just told you why it should work, because thanks to the generic vanishing theorem, we know that this V1 locus is quite small. But first of all, if you want to do induction until you reduce to curves, you have to start again with an effective divisor at the next step, at least in the same algebraic equivalence class of D. And so...
understand, sorry. You are at D. D is effective. Then 0 is an isolated point. So here there is nothing. If D restricted to D is not effective, there is nothing to prove.
No, what I'm saying, the easy, let's not say easy, but the case that is well understood in Brill-Noether theory is curves. So it's sort of tempting to say, okay, I have a threefold. Then I take a divisor. I look at the Brill-Noether locus of this divisor, which is a surface. But how do I understand the Brill-Noether locus on a surface? I cut again, go down to a curve.
The question I'm asking, I hope I'm not wrong. If D restricted to D is not effective, there is nothing to prove. So you might...
No, because I'm...
If you go back to the exact sequence before, sorry.
Trying to generalize the sheafification. Trying to do this.
You take eta equals 0.
Argument of Kempf.
Yes, for eta equals 0, this section tells you nothing.
If there is no for it, take eta equals 0. If there are no sections there is just.
Okay, but there could be a locus not that point, but there could be a big component somewhere else, and I'm interested in understanding the old Brill-Noether locus.
It's obvious to make this assumption that D restricted to D is effective.
Okay, but
because it's a normal bundle which it moves.
But I think we'll better discuss this when you've seen what I'm aiming at. But what I was saying is that the easier way is to do such an induction. You would assume you already have a certain number of sections of D, so you can go down cutting. But then this is not going, of course it's going to work, but it's not going to give you very interesting statements, because we became to be interested in this type of problems for curves on surfaces, and we wanted, and our main question was, we have a curve, we know that it has no sections. Does it move at least algebraically? So if the effective way to know that there are enough sections usually is some kind of ampleness, some positivity of D. And then if you have positivity, all the problem is sort of solved, because you can use vanishing theorems and the number of sections will, this is philosophical, but it's likely to be constant. So it doesn't make, it's not very interesting. I'm not saying it cannot be done. And for the same reason, you don't want to assume D is smooth to start with, because again, this is sort of a strong assumption. It would not give us the kind of applications we were looking for. And so this is where you get stuck if you start working at the problem like this. And of course, if you start with a surface, then D is a curve, and then the condition that there is an algebraically there is a divisor which is effective and algebraically equivalent to your given one is no problem. You just need the self-intersection of the divisor to be positive. And then in the case of surfaces, we've been able to somehow work around problem 2. and avoid assuming smoothness. And so the sum of these two facts is that, in fact, we have an existence theorem and connectedness theorem for curves on surfaces. Let me. Okay, now, first of all, I was going to explain how is it possible to avoid working only with smooth curves. So you just consider now an abstract curve. In my applications, it will be a curve on a surface, but it doesn't have to be. And it's reduced, connected, and then you know that the Jacobian of the curve has a compact part, which is the product of the Jacobians of the normalizations, and the kernel of this natural map is a linear group. And then the key observation here, which is a very simple one, is that we it's not useful for us to work with the all Picard group, which is not compact. But it is enough for us to understand what happens on a compact subgroup. That, in our case, will be the peak zero of the surface we are considering. So to this data, we add a compact subgroup of some dimension t, and we write down a Brill-Noether number that is exactly the same as before. It's the dimension of the subtorus of the compact subgroup minus h1 times h0 times h1, where since the curve is not smooth, we have replaced genus by arithmetic genus. And what we are able to prove is that instead of looking at the full Brill-Noether locus, you just look at the intersection of the Brill-Noether locus with T. So the situation is above, and then I fix a line bundle on C. Then the Brill-Noether locus works exactly as in the smooth curve case. You have existence. As soon as the Brill-Noether locus is non-negative, then this locus is non-empty. And you also have connectedness.
Who is L?
L is written here, I think, is a fixed line bundle of degree D on the curve.
Doesn't make sense.
Why?
There's supposed to be a line bundle on the surface.
Not yet, not in this slide.
Oh, I see. You're only doing the curve.
I'm doing the curve. I was just trying to say how we work around this difficulty of working with. I will apply it to a curve on a surface, but for the moment, and T will be peak zero.
So the degree is the sum of the degrees of the...
I don't really care. So yes, it's the sum of the degrees. It's the so-called total degree.
So whatever occurs in Riemann row.
Exactly. Precisely. And this is nothing difficult. Just take the proof by Fulton and Lazarsfeld. It's explained very well in Lazarsfeld's book, Positivity on Algebraic Varieties. And it works. It works, but I forgot to point this out. There is an extra assumption here. So T, of course, T being compact goes finite to 1 onto the compact part. But it might be possible that the map to one of these components, peak zero, C tilde I, that may have positive dimensional fibers. And we want to avoid that, so we assume that this does not happen. Because, as I was saying, the proofs imitates Fulton and Lazarsfeld. We prove positivity of a certain vector bundle on the curve C, which is constructed exactly in the same way. And this vector bundle is not positive unless you make this assumption, which is not to say that the statement is not true. What we can see is that the proof fails.
It's positive of the product of the curves.
I had this E to F, and I want that the vector bundle hom E to F is positive on T, because that's where I work, which is a very nice torus projective, so no problems with open parts or anything. And as I was saying, it's definitely true that if you don't put that assumption, then the vector bundle is not positive. But there might be a better proof that works also. We don't have geometric counterexamples without this assumption.
And it will be semi-positive because it has
exactly.
So
I don't know. We thought about it for a while and could not do better. Sorry. So now we have all the ingredients to prove our theorem for surfaces and so also to state it. So I take a smooth surface with the irregularity Q, and now C is a curve on the surface, reduced, connected, and I assume that Ci square is greater than 0 for every I, and this is exactly the condition I was talking about right now. This gives me that the map from peak 0s to peak 0 of Ci is injective. And then we define a suitable Brill-Noether number here, which is exactly the previous Brill-Noether number in the case of the line bundle given by C restricted to C. So D is replaced by the self-intersection of C. This is the geometric genus, and Q is the dimension of peak 0 of the surface, which is the compact subgroup I will be looking at. And again, the R equals 0 case here is maybe the most interesting for us, and so in this case I just dropped the R and I wrote it. I just write rho of C. So I've basically given you the proof. In any case, I'm not going to give any more details. We put together all the previous remarks, and we obtain an existence theorem for surfaces. So we assume that as no irrational pencil of genus greater than 1, in order to exploit the description of V1, and then we have some alternative assumptions. If you think about this, I will comment on this, but if you think about the assumptions for a moment, you see that they all have the same purpose. You want to compare the Brill-Noether locus on the curve with the complement of the cohomology vanishing, the cohomological support loci. So the first possible assumption is that this number is greater than 1. And then you compare by dimension, because we know that V1 has dimension at most 1, so it cannot contain the Brill-Noether locus. Or V1 does not generate peak 0 of S, and again, since the Brill-Noether locus generates, then you can compare and say they are not the same. And then in these cases, you have existence. Sorry, I don't understand this thing so well. And then the second point is more precise, because as Fabrizio was remarking before, it's not clear that L itself belongs to the Brill-Noether locus on the curve. So since we are interested in actually moving a curve, it's important for us to know. And then we have this more precise statement in the R equals 0 case. So this assumption is the same as before, or this is a new one. This is sort of weak. It's quite easy to fulfill. So you ask for rho to be at least to be 1 or more, but if it's greater than 1, then you are in this situation. And it is enough that C is not contained in the ramification locus of the Albanese map. Or again, for rho of C equal 1, you ask for that V1OS does not generate, then we have a more precise statement. not only this has the expected dimension, but there is a component of this dimension that contains 0. So, as I was saying, for instance, if you have a curve with h0 of c equal 1, so a curve that does not move linearly, then you have some kind of sufficient condition for the curve to move, at least algebraically. And yes, as I wrote this not to forget, because I think Margherita will talk in general about curves on irregular surfaces, and I think she will mention some applications of this result. And some remarks about this statement. First of all, the assumption. The assumption that V1S does not generate peak 0 is one of the possible assumptions in both in 1 and 2. And this is not a very strong assumption either, because if V1 generates peak 0, then up to isogeny, it means that peak 0 is a product of elliptic curves. So the peak or the Albanese of S are very special, so it doesn't look like very restrictive assumptions. In fact, at some point we thought maybe this never happens. In fact, it does happen in some cases, so it's not a vacuous assumption either, but I think it's not too restrictive. And this I have already explained. This assumption is needed to make to be able to use the result on Brill-Noether loci for singular curves. And the statement is sharp, at least in some cases. This is sort of the classical case one always gives when you want to show an example of an irregular surface with a curve that moves algebraically but not linearly. Take a symmetric product. There are these so-called coordinate curves, which means symmetric product you can think of as degree 2 effective divisors. You look at divisors that contain one fixed point. Basically, you get a copy of D inside D, and if you change the point, it moves in a one-dimensional family. And if you compute the Brill-Noether number, in this case, you get the exact answer, which is 1. So it's not too bad, but not so good either, because we have tried to apply this theorem to several cases, examples of curves we knew in irregular surfaces. As already Pietro said, somehow there are not so many known examples of irregular surfaces. And when you test the theorem against these cases, very often the Brill-Noether number is smaller than the actual dimension. But this is not due, I think, it's not a problem of the method. Because the fact is that you are given a numerical statement. Cannot be really a subtle statement, it's just a number. And in some cases, we sort of identify our Brill-Noether locus with the Brill-Noether locus on a curve. If the curve is not Brill-Noether general in moduli, then the Brill-Noether number will not give you the right answer. And however, we also have problems for r equals 0, where this, of course, every curve is Brill-Noether general in that sense. And it's some kind of, I put it there as lack of transversality. So it's somehow peak 0 is in special position inside the peak of the curve with respect to the symmetric product of the curve. And again, you cannot hope to detect this kind of phenomena just writing down a number. So it's, we were a bit disappointed when we realized that it was not such a good Brill-Noether number in many examples, but I don't think if you want to encode everything in a number that you can do much better than this.
The VBAC people have more or less the same problem with vector bundles. So they write down the Brill-Noether number, and sometimes, sometimes everything is superabundant.
Yes, and this happens often because you look at very special curves, and so it's built into the applications. And then I would like to ask. Oh, I don't have that much time. How much do I have left? I don't know how I started. Less than 10 minutes, okay. Because, yeah? 10. Not 2 minutes, I would just walk down. Okay. No, I just wanted to tell you something about the number one. You remember I said we did two things, some infinitesimal study and this existence theorem for surfaces. And so I would like to recall this is a result of Shao, goes back to 1987. And you have a surface of maximal Albanese dimension and a fibration over P1. It's important that it's over P1. Then he gave a lower bound for the geometric genus of the general fiber in terms of the irregularity. So let me just tell you how he did this. First of all, the main step in the proof of this theorem is to bound from below the H0 of Ks restricted to F. And he proved that it is at least Q minus 1. Then you can look at the adjunction sequence on the surface. And you have this restriction map. And then you have a subspace. You multiply sections here, but at least you have at least one section here because F moves in a pencil. And then you get a subspace inside the image of dimension at least Q minus 1. And then now you look at the next step in the same exact sequence. You know that the image of this map is at least Q minus 1. This is surjective. So you get a bound for the dimension of this space, which is Q minus 1 plus Q. So that's how Shao gets to Q minus 1. So sorry. Hope I didn't break it. Maybe, I think I did, actually. Can you hear me, even without the microphone?
It seems the first assumption is not necessary.
Sorry?
Without the first assumption, in Shell's theory, S is not necessarily the maximum of this map.
Mm-hmm. Now, the assumptions are as stated here. Surface has maximal Albanese dimension, irregularity Q, and you have a fibration.
You want to use in this case?
Sorry? No, but this is a fibration over P1. Yeah. It's not what I exclude is fibrations over a curve of genus at least 2.
No, but Shell's theorem doesn't need the maximum Albanese dimension, right? The Shell's theorem.
I think so. You have to wedge two forms.
For this statement, yes. No, the theorem of
I'm sorry. Okay, but he has a different argument then. Oh, sorry. Okay, thank you. Thank you. I didn't check carefully. Thank you very much. And so our idea was trying to see what can you say in general for a similar situation. So you have a variety of maximal Albanese dimension, irregular, and in a reducible effective divisor. And in fact, you can weaken Shell's assumptions. In order to prove this crucial step here, you don't really need that F moves in a linear system. That you use here, and then to conclude. But to prove this, we realized that it is enough that F is not in the ramification locus of the Albanese map. So we start with the same situation, but any dimension. So we take in the we wanted to generate the Albanese variety, which was automatic in the previous assumptions. And we get an analog of the two steps in the proof of Shao, because we give a similar bound for the image of the restriction map from H0 of Kx to its restriction to D, and this is Q minus n plus 1, so when n is equal to, it gives you Q minus 1, which is what we had previously. And then we look at the next step in the restriction sequence. We have H0 of Kx plus D, H0 of Kd, H1 of K, next will be H1 of K plus D, but then in this case we have no vanishing. So we, while in the other case the map was automatically surjective, we have to take care also of the rank of this map. And we can give a similar bound, a lower bound for the co-rank, for the rank of the image of the next map, which is Q minus n plus 2. This is, as I already explained, the step 2 is necessary because we do not have vanishing. And the proof of 1 is just taking, we want to bound the dimension of the image of global forms on the surface inside this space. We look at a subspace, which is which are the global n forms that are obtained by wedging global 1 forms, and then one can prove that the rank of this is at least Q minus n plus 1. And as I put it, this is linear algebra, not the kind of linear algebra you teach in first year, but still somehow it is linear algebra. This has nothing to do yet with Brill-Noether loci. And then the proof of 2 is similar. And so, yes, first of all, one would like to know what happens if D is contained in the Albanese, in the ramification divisor of the Albanese map. Because you see, this map is 0 in this case. The ramification divisor of the Albanese map is, you could define as the locus of where you could characterize the divisor, the fact that a divisor is inside the ramification locus of the Albanese just by saying that this map is 0. And so this method just breaks down completely. Still, we do not know whether the statement still holds. We have tried with surfaces and curves on surfaces, and we could not find any example where this bound did not hold. So this, I think, is an interesting question, because this is the key point that you need in the Brill-Noether existence theorem for surfaces to say that 0 is in the Brill-Noether locus. So I don't know if anybody has suggestions about this. And the 2 bounds before give you a generalization of Shao inequality to higher dimension. You just add the 2 bounds, and so if you have a divisor, in a reducible divisor that moves in a linear system, then you have this bound. If R equal 1, you recover the Shaw's bound. N equals 2 and R equal 1, you recover the original Shaw's bound. And if you have more section, of course, you get a better bound. And the last thing I wanted to explain is that these bounds can be improved if we have some knowledge of the Brill-Noether loci. You can get significantly better bounds. So So let me do this quickly. Again, we have the tangent space is given by the same map as before. Again, we have a Petri map, which is defined exactly in the same way as before, but because dimensions are higher, we cannot say that the image of beta is orthogonal to the tangent space, but it is orthogonal to this subspace that is related to the tangent space. But in some sense, the Petri map still controls the geometry of the Brill-Noether loci. In fact, you see the image of the Petri map is orthogonal to the image of this subspace. So if T is big, you expect that the image will be big, and so the tangent space will be small, and conversely, of course. And if you have a lower bound, if you have an upper bound for kx minus d, this is the same as a lower bound for this image, which is what we are really interested in. So again, you assume that you have no irrational vibration, and that the X assumption here is that the tangent space to the Brill-Noether locus is positive dimensional. So the divisor moves at least infinitesimally. And then we can get better bound for the two maps that come into writing down the inequality. Actually, no, for one. The other one we use the previous bound. And then I think I'm out of time. And yes, I was to here I make a stronger assumption as before. I'm not only excluding pencils, but any kind of irrational vibrations. And this can be detected. It's a famous theorem, generalized Castelnuovo theorem, I think is due independently to Fabrizio, Green-Lazarsfeld, and Rahn, or I don't know exactly the priorities, but the main point is that this geometrical condition you can understand, again, let's say by linear algebra, just looking at wedge products of forms. And then, granted this, and using the Petri map, again, you do some advanced linear algebra and prove this theorem. And so let me finish by just stating this generalized Shao inequality that we obtain when the tangent space to the Brill-Noether locus is positive dimensional. I think I've done something stupid here, yes. Okay, and so I think you should look mainly at 2, because this is sort of less interesting. This means that D is big enough, so you have other ways to control the theory. And you see the bounds that one obtains are significantly better, because you for n equals 2 you get the improvement is that you get this dimension of t here. So if the curve moves infinitesimally in some not linearly, you have a better bound. And for n greater than 2, this is definitely much better, because Shaw's inequality, even in the generalized form, was 2q times terms. Maybe I've written it down. Yes. So for n greater than or equal to 3, the coefficient here is n plus 1 instead of 2. So it's for q big is definitely much better than the uniform bound that you can get without knowing anything about Brill-Noether loci. Okay, I think I'm already over time, so thank you for your patience.
Thank you, Rita. Are there questions?